Hello, my name is Connor Brandon, and today I'm going to explain the difference between the way a computer stores numbers it will be performing arithmetic on opposed to the way a computer stores numbers it will be displaying for humans to read. A simple way of showing you is to use a calculator. The calculator on Windows 7 has many options. To get to it, just go to Start, type in Calculator, and once you get to that, you should have the basic calculator. To get to the advanced one, click View, go to Programmer, and you should have what many programmers use and what the computer can actually read, which is binary, which should be displayed right here if I type any numbers. Now, say I put in 7. The binary code equivalent is shown right here. This is what the computer reads, and when performed arithmetic on, say, plus 5. The 7 is gone, and now the 5 equivalent in binary is shown. This is because the 7 is put into storage, and the 5 is now being shown. Now, 7 plus 5, as we all know, is 12. And the 12 equivalent in binary is shown right here. Now, if I put in any sort of number, it will display the binary equivalent up to, I think, about 8 bytes. So all this code is the binary equivalent of this massive number, which is stored in base 2. When computers store numbers, it's always in binary. However, assemblers such as PEP8 like to store numbers differently from base 2 and base 10 in a form called hexadecimal. Hexadecimal is a series of letters and numbers that can compress binary code more efficiently for computers to read. Computers, as you know, only use base 2, so 1s and 0s, making it hard for them to display base 10 numbers. This is why assemblers were made to bridge the gap, making it easier on computers and people. Now, if we open a script-based program such as Microsoft Word or Notepad, we can see just by typing the number 10 that it automatically displays in base 10, or even with letters, such as ASDF. This is because the computer already has stored in the system binary that corresponds with the letters or numbers. This is a key and combination in the ASCII 2 table. This stands for American Standard Code for Information Interchange, which shows how characters are represented by 7 digits in base 2 numbers. Each of these sets of 7 digits is equivalent to a symbol or a number or letter, such as A, the number 1, or even the @ symbol. Now, the symbols don't correlate or mess with each other, but they are just outputted as a series of bits and bytes that the computer just shows on the screen. They can be saved in the same format as binary for the computer to read at a later date. And this is the difference between how computers store binary arithmetic and how they show in base 10 and base 2.